So sometimes when you are driving a car, let's say, and there's another car which is approaching you, like here, for example. So if the car is really far, you will not be able to say that this is a car. So maybe you will think about this car as if it's a motorcycle. And why is this? Because the two sources of light from this car will appear to your eye as if it's one. And of course, as this car get closer to you, you will be able to resolve these two sources that they are two distinct sources of light. So in this lesson, we're going to learn when do we or why do we sometimes not able to resolve two objects that they are two distinct objects. But before discussing all of this, I'm going to talk about how do we really see. So how do we see? For example, let's say that there's a source of light, and this is my eye. Of course, this is not to scale. So this opening, it's the aperture of my eye, and here there's the retina of my eye. So what will happen is that light from this source is going to be emitted and it will enter through the aperture of my eye, and what will happen is that light is going to diffract. So you will learn, or you learned in topic 9.2, that whenever a light passes through a hole, it's going to, or through an opening, it's going to diffract. Okay, so diffraction is going to occur, and what will happen is that the interference pattern, the diffraction interference pattern, will be formed on the retina of your eye. So basically, this central maximum here, this central maximum with the maximum intensity, this is as if it's the image of this object in your eye. So this is how we see. Now, what if instead of having one source of light, what if I have two sources of light? So of course, this is my eye, the aperture of my eye, and this is the retina. What will happen is that light will come from the source, from this first source, let's say, so it will come into the aperture of my eye, and interference pattern is going to be formed. So I'm going to take this and duplicate it so that I can place it here. So let's say this is the interference pattern, the diffraction interference pattern due to the first source. Now, for the second source, the same thing is going to happen. Okay, so light is going to come from the second source and it's going to diffract, and what will happen is that another intensity pattern is going to be formed. So this is the second intensity pattern for the second object. Now in this case, if the interference pattern, if the diffraction patterns, it looks like this, then my eye or my brain can tell that these two sources are actually two. But if, for example, the interference pattern is something like this, okay, so look at this spot. I'm looking at this yellow spot here. Okay, so here I can tell that they are actually two. But now look what will happen if this interference pattern is going to get closer. So what will happen is that these two sources are going to get closer. So if they get closer to one another, then this intensity pattern is going to get closer. So let's say that it gets closer in such a way that it reaches this point. Let me make it a bit more. Okay, so it reaches this point. So in this case, so this will be the light coming from the second source. Okay, in this case, we say that these two objects are just resolved. Okay, so I can just tell that they are two objects. But if this interference pattern is more close than that, then in this case, look at it, I can't tell that they are two objects anymore. It looks like it's one. Can you see? So my criteria in order to tell if the object is just resolved or well resolved or not resolved is called the Rayleigh criteria. So what does this criteria state? It states that if the central max, if the central max of the first source is on the first minimum of the second source, then this means that the two objects will be just resolved. So look here, this is the max from the first source. It's on the first minimum of the second source. So if this is the situation, then we say that the two objects are just resolved. So we can just say that these two objects are really two. And this is the Rayleigh criteria. So let's look into it using this diagram. So for example, as I was discussing, as I said, if the maximum, so this is the interference pattern from one object, and this is the interference pattern from the second object. Now, as you can see, if the central max of the first is on the minimum of the second, okay, and the same thing will goes here, then this means that I can just resolve these two objects. So from this image, I can tell that there are two sources. It's not one, but here it's just resolved. If this distance is increased between them, okay, so now the maximum is not on the first minimum. Look, it's on the first maximum. So in this case, it's well resolved. So here I can say that it's well resolved. But in this case, it's just resolved. Here, it's not resolved at all. So in another word, in order for the two objects to be resolved or just resolved, let me try to do the light rays here. Okay, so look, in order to tell or to say that these two objects are distinct, then this angle right here should be, which is the angle between the two maximum of the interference pattern, should be equal to a certain value, which is called the critical angle. Okay, so if this angle, and I'm going to find what's this critical angle later, if this angle, which is the angle subtended from the two sources, because these two angles are vertically opposite, so the angle which is subtended from the two sources, okay, it's the same angle between the two maximum. So if this angle is more than theta c, we say that it's well resolved. And if this angle is equal to theta c, we say that it's just resolved. But of course, if theta is less than theta c, we say that it's not resolved. Okay, so for the object to be resolved, I should follow the Rayleigh criteria. Okay, so you have to memorize the statement for the Rayleigh criteria. Now let's do some analysis for what's happening. So I need to find what's this theta c. So what should be the value of the angle which should be equal to theta c in order for the object to be resolved. So let's check. So let's say that I have here a light coming from the first source and it's hitting the retina of my eye, and I have here another ray coming from the second source and it's hitting the retina of the eye. So let's say that this is the interference pattern for the second source. Okay, and this is the interference pattern from the first source. So in this case, of course, it will be well resolved. So let me consider the case where it's just resolved. And why I'm doing this, because I need to find what's theta c. So I'm going to erase these two rays and I'm going to try to draw them again in such a way that the objects are just resolved. So this is the criteria. So here, as you can see, the maximum here, the maximum of the first is on the minimum of the second, and the same thing goes here. So this is the two sources. Okay, and let me try drawing it using a line. It will be easier for me. So this is the ray from the first source hitting towards my retina. Okay, and I'm going to draw another ray. So another ray from the second source. Okay, and let me move the aperture of my eye a bit somewhere here. Okay, so here there should be the aperture of my eye. Okay, so let's say that the opening of my eye, I'm going to call it B. So this is the diameter of the eye. This is the separation between the two sources, it's D. Let's say that the distance from the source to the retina, it's D1. And the distance from the retina to my eye, sorry, D1 is from the source to the aperture, and D2 is from the aperture to the retina. Okay, so in this case, since the max is on the min, so this angle right here, it's called theta c. It takes the value of theta c, but also this angle is equal to this one because they are vertically opposite. So this theta, it's the angle subtended from the two sources towards the aperture of my eye, which is equal to the angle from between the max and the min, or between the two maxes, because here the max is on the min. So what I need to do is that I need to find what's theta c. So in this case, theta c, which is the critical angle, it's equal to, let me just remind you of something. In a diffraction pattern, if you remember, we said that the condition to have a destructive interference is the following, which states that the opening of the aperture times sine theta, but usually for small angles we approximate sine theta as theta, and it's equal to lambda. So this is a condition to find the angular separation between the maximum and any minimum. So if we take m equal to 1, I'm talking about the first minimum because this is the case. So here I'll be finding the angle between the maximum and the first minimum, which is this angle, the one that I'm talking about here. So in this case, the theta here is going to be equal to lambda over b, and this is the critical angle that I'm talking about. So if the angle subtended from the two sources toward my eye is equal to the critical angle, which is equal to the wavelength of light over the opening of my eye, or the diameter of the aperture. So in this case, if the angle is equal to this, then the two objects are well resolved, or basically, sorry, it's just resolved. Okay, I can also find the critical angle by using another physical quantity, which is the distance between the minimum and the maximum, which is this s. Okay, so I can, instead of theta c, I can write s over d2, because we approximated for small angles that theta is equal to tan theta, it's equal to sine theta. So if you talk about tan theta, so it's the opposite over the adjacent. So in this case, I can replace theta c by s over d2, or as well, I can replace it by d over d2. So I can write it as d over d2. And in this case, this will be also equal to lambda over b. So what are these? This distance here, as you said, it's the distance from the aperture of the eye toward the retina. This is the distance from the sources toward the eye. This is the separation between the sources. This is the distance from the central max to the first minimum. This is the wavelength of light, and this is the size of the aperture. Now, for the eye, because it's considered to be a circular aperture, we should add here 1.22. Okay, so basically this is the critical angle at which I can just resolve two objects from one another. So for a higher resolution, theta c should take a small value. So the less the theta c, the more the more the resolution of the instrument. So for example, if you look here, for example, at this equation, in order to decrease the value of theta c, I can either use a smaller wavelength light, which will decrease theta c, or I can use a wider aperture size. So let's look into real life examples here. For the radio telescope, because the waves that are approaching are in the radio wavelength, which is a very high lambda, so for theta critical to be less, since it has a large lambda, so I have to use a very large aperture. So that's why a B has to be large. So since lambda is big, B should be big, and that's why theta C will take a less value, which means that the resolution is going to get more. Now for this, which is the electron telescope, since the aperture is small, so B is small, then I have to use a small wavelength, and that's why we use the electrons in the electron telescope, because it has a really small wavelength, which will increase the resolution. So if you were asked, for example, which light will give you a higher resolution, is it the red or is it the blue? So in this case, you have to look at theta c. Which one has a smaller theta c? Blue will have a smaller theta c because lambda is less, which means that the resolution using the blue is going to be more than that of a red. Okay, and so on. So that's it for the resolution. That's it. Okay, so the next video is going to be on solving some examples, and we still have the resolution of the diffraction grating, and that's it. So in order to resolve two objects, that they are two distinct objects, the angle subtended from the two sources, this angle should be equal to theta c. What is theta c, or how do we find theta c? We find it using this equation. Theta c, it's the wavelength over b, or we have to multiply it by 1.22 if the aperture is a circular one. Okay, and we can check, or we can, sometimes you will be asked, for example, at what distance we will be able to resolve and so on. So we will be forced to use this equation. By the way, this is D1, it's not D2. So that's it.